Hi everybody, this is our lecture on section 4.6, which is on directional derivatives. So given a two-variable function, f, x, y, we defined the partial derivative with respect to x is the limit as h goes to 0. So x varies by h, but y is constant. Oops. X is varying by h, but y stays the same. So the partial derivative with respect to x is really just the ordinary single variable derivative where the letter y represents a constant. Partial derivative with respect to y is defined similarly. fxy plus h minus fxy over h. So this time x is designated to be constant and y is varying by h. Okay, so here x plus h comma y, right, this is equal to xy plus h times the unit vector 1, 0. And then x comma y plus h, right, this quantity that we're looking at here and here, is equal to xy plus h times 0, 1. Right? This is the derivative in the I direction. I equals 1, 0. The partial derivative come on. To get the partial derivative in the I equal to 1, 0 direction. And here, to get the partial derivative in the j, which is 0, 1 direction. But what about any other direction? So now consider any other unit vector given by unit vector u equal to cd. You know, and what was the deal with unit vectors? The length of the unit vector is equal to square root c squared plus d squared equals 1. Right? That is just c squared plus d squared is 1 squared, which is just 1. Right? That's what defines unit vector. And now define the, let me do it on the next page. Define the directional derivative for u as follows. So we denote it, the notation is not so great, but it's capital D for derivative in the direction of u of the function f xy. All right, and that's going to be equal to, well, again, it's the same kind of thing. The limit as h goes to 0, f and x plus ch, comma, y plus dh. So you split up that h, c% of it in the x direction, d% of it in the y direction, instead of 100% in the x direction and 100% in the y direction. Minus fxy over h. All right, well, actually, let's do it in terms of constants, a and b. Oops. So this is a, and this is b. All right, so we're doing it in terms of the constants a and b instead of variable x and y. So very similar to these, right? Here the h is with x, here the h is with y, right? Where you think of this as xy plus h times 1, 0, and you think of this as xy plus h times 0, 1. Here, oops, where now a plus ch, comma, b plus dh is equal to ab plus h times u, where u is the unit vector in whatever direction that you want. Okay, now before we get into calculating that, what does it mean geometrically? Well, geometrically, the partial derivative for f with respect to x and the partial derivative of f with respect to y were the slopes of these lines, these curves on that surface. So the tangent lines on the surface the lines on the surface, the curves, the lines that are tangent to the curves in the x direction and the line tangent to the curves in the y direction. So the orange one, that is the 1, 0 direction, right? That's the direction I. The purple one, that's in the j direction. Let's see if I can make that more. Yeah, that's in the j direction. And now we have the u direction. So we'll make the u direction, what color? We're running out of colors here. Make this icy blue here. So now u is in this direction here, say. All right, so that unit vector u is in that direction, and then the slope of this line, this tangent line to the surface, which follows this curve on the surface in the u direction. So here the slope, this word domain here, slope is equal to the directional derivative for f in the direction of u. And you can do that for any direction. So you've got a whole circle of different directions that you can pick. Right? You have this direction. You also have the opposite direction. And it doesn't give you the same slope. It gives you the negative slope. Because in this direction, it's the slope, going down, in this picture anyway. And in this direction, it's that same slope going up. So they're negatives of each other when you turn it around. Like that. So how do you calculate this thing? Not as difficult as it might seem. So the derivative in the direction of u, the directional derivative in the direction of u, is the slope of the surface z equal to fxy at AB in the direction at AB, FAB, of u. Okay? So how do we calculate the directional derivative? Okay, well, go back to the definition for a moment. The definition of the directional derivative is right here. Oops. So the definition is like this. So notice, since a and b are constants, is a constant point. Since a and b are a constant point, f a plus ch comma b plus d h is just some function, single variable function in h, where x is equal to a plus ch and y is equal to b plus d h. So the directional derivative of f at AB is just the derivative with respect to h, the single variable derivative with respect to h of this single variable function in terms of h. Well, we'll just call it f of h. So how do we calculate that? How do we calculate that? We calculate it using the chain rule, right? That's exactly what we learned in the last section. So we have that f is a function in terms of x and y, and x, right, which is a plus ch, is a function in h, and y, which is equal to c plus dh, is also just a function in h. Right? A and c and b and d, those are all constants. So f is in terms of x and y are both in terms of h. So the directional derivative of FAB is the derivative of f with respect to h, which is equal to the partial derivative with respect to x times dx dh, plus the partial derivative of f with respect to y dy dh, right, where x is equal to a plus ch and y is b plus dh, sorry, b plus dh. Well, dx dh is what? Dx dh, h is the variable and c is a constant, so it's just c. So this is df dx times c plus df dy, and then the derivative of y with respect to h is just d. b is a constant, d is the coefficient of h. So this is equal to this dot product. Oops, I used the d instead of this thing. partial derivative of f with respect to x, comma, partial derivative of f with respect to y, dot c d. This vector here this is u, and this vector right here is called the gradient of f. The gradient vector for f, x, y is, and then you write it like this, point down triangle, partial f with respect to x, comma, partial f with respect to y. So this is equal to the gradient of f dot u. CD is u. All right, so in summary, the directional derivative of f at AB in the direction of u is the gradient of f dot u. So that's how you calculate the directional derivative. The geometric meaning of the directional derivative as the slope of the surface, in the direction of u, right? That comes from the limit definition of the directional derivative. All right. So that's how you calculate the directional derivative. Let's rewrite the dot product in terms of the sine and cosine. Okay, remember also that the derivative with respect to u of FAB, which is equal to the gradient of fxy dot u is equal to, well, and let's just drop the fxy now. It's the length of the gradient times the length of u times cosine theta, where theta is the angle between the gradient and u. But the length of u is just 1, because u is a unit vector. So this is equal to just the length of the gradient of f times cosine theta. So, well, that's interesting. What now is the length of the directional derivative? The length of the directional derivative is just the length of the gradient times cosine theta. So the length of the directional derivative is equal to, well, we don't have to say it that way. So the value of the directional derivative is just the gradient times cosine theta. So the largest value for the directional derivative of FAB is the length of the gradient, which happens in the direction of the gradient when theta is 0. The direction of that, i.e., when theta is 0 degrees. The smallest possible value for the directional derivative is the negative of the length of the gradient, which happens in the opposite direction. In the direction opposite to the gradient of f, i.e. when theta is 180 degrees. And also, the directional derivative is 0 when u is perpendicular to the gradient. i.e. when theta is 90 degrees. So if you look back to that picture, right, you've got all these different directions to choose from. You've got all these different directions to choose from for the directional derivative. A whole 180 degree rotation, or 360 degree rotation. So you have this tangent plane around that point of tangency. Maybe I should leave those lines in there. You have this whole tangent plane at that point, and you can find the slope of the vector in the tangent plane at that point for any angle that you'd like. Right? And at some point you're going to have a maximum. At some point you're going to have a minimum, which is going to be the negative value of the maximum. And then some two places in the middle you'll have a horizontal slope, the derivative equal to 0. So let's take an example. So let's take the saddle surface, z equal to x squared minus y squared. So at xy equal to 1, 2, find the directional derivatives for u equal to 1, 0, 0, 1, 3/5, 4/5. Yeah, those three there. Maybe we'll do one more. 3/5, 4/5. What else? 1 over root 2, 1 over root 2. Okay, in which direction is the directional derivative the largest? what is this largest value? And in what direction is it 0? Okay? So first of all, we calculate the gradient. So the derivative of z with respect to x is 2x. And the derivative of z with respect to y is minus 2y. So at the point 1, 2, right, so you can calculate the gradient in terms of x and y, or you can calculate it for the specific point. So zx, the gradient of f in terms of xy is 2x minus 2y. So the gradient of f in terms of the point 1, 2 is 2 minus 4. Okay? 2 minus 4. So now the directional derivative in the direction of 1, 0 of z xy is equal to, well, the gradient of f dot 1, 0. Right, which is just equal to 2. Right, which is the derivative of z with respect to x at the point 1, 2. And the derivative 0, 1 in the 0, 1 direction of z, not xy, 1, 2 is equal to the gradient of f dot 0, 1, and that's equal to negative 4, and that's just the derivative of z with respect to y, partial derivative of z with respect to y at 1, 2. The directional derivative in the direction of 3/5 minus 4/5 of z 1, 2 is equal to, well, the gradient, actually there's no f, gradient of z dot 3/5 minus 4/5. So that is 2 minus 4 dot 3/5 minus 4/5. So that's equal to 6 minus 16, so minus 10/5, which is minus 2. And the directional derivative in this direction of z 1, 2 is equal to the gradient of z dot 1 over root 2, 1 over root 2. So that's 2 minus 4 dot 1 over root 2, 1 over root 2. So that's equal to minus 2 over square root 2. So we have several values for the directional derivatives. In the x direction, or the I direction, is 2. J direction is negative 4. In this direction, 3/5 minus 4/5 is negative 2. And the direction 1 over root 2, 1 over root 2, it's minus 2 over square root 2. What is, second part of the question, in which direction is the directional derivative the largest? And what is this largest value? And then in which direction is the directional derivative 0? So remember how we just showed up above. The directional derivative, another way to calculate it, aside from just the dot product, gradient dot, and it's supposed to be AB there, isn't it? gradient dot u, it's also just the length of the gradient times cosine theta, because the length of u is just 1. So the largest possible value is the length of the gradient vector. Smallest possible value is the negative of the length of the gradient vector, and the directional derivative is 0 in the direction u that's perpendicular to the gradient, when the dot product is 0, that is. So here, the largest possible value for the directional derivative is just the length of the gradient f. Let's see. Is this, which is the length of, what was it, 2 negative 4? 2 minus 4, which is 2 square root 3, right? That is square root of 4 plus 16, square root 20 at 2 square root 5, excuse me, in the direction u equal to, well, 2, 4. Right, but of course you got to divide by the length to make it a unit vector. And the directional derivative is 0 in the directions perpendicular to 1 over 2 root 5, 2 minus 4. And those directions are, now by the way, you don't have to state it as a unit vector. You could just say it in this direction. In the direction 2 minus 4, you know, or 1 over 2 root 5, 2 minus 4. But that's just the same direction, just making it a unit vector. And the directions perpendicular to this, which are, well, how do you get perpendicular vector to that? You switch x and y and you negate one of the coordinates. 4, 2, and minus 4, minus 2, right, which is 180 degrees apart from each other. Right, and the dot product of this and that is 0, because it's 4 times 2 is 8, minus 4 times 2, which is 8. And this is negative 4 times 2, which is negative 8, plus negative 2 times negative 4, which is positive 8. All right. Now what else? What other sort of interesting properties does the directional derivative have? So the gradient vector and level curves. Given a level curve, k equal to fxy for the function z equal to fxy, right? The slope of the curve at, any given point is dy dx for, where y is implicitly a function of x in the mixed equation k equal to fxy. So here's the picture. Right, and at this point here, xy, the slope of that tangent line, the slope of that tangent line is dy dx, which is equal to what? Right, which is equal to, as shown in the previous section, right, negative the partial derivative of f with respect to x over, so this is the rise, no, y. Right, this is the rise, this is the run. Yeah. Which was shown in the last section on the chain rule. Right, so the vector in the direction of the line for the tangent line is rise over the run. So rise is the change in, no, the rise is the change in y. Now I've got this backwards. Yeah. Rise is the change in y. So that's minus fy over the change in x, fx. Well, what is this vector? This vector is exactly perpendicular to the gradient. But the gradient of fxy is equal to partial derivative of f with respect to x times partial derivative of f with respect to y, which is perpendicular to the tangent line with slope vector minus fy fx. So here's the picture. So this is the gradient vector, which has slope, which is the vector fx, fy, partial derivative of f with respect to x, partial derivative of f with respect to y, and this is the tangent, which is minus the partial with respect to y comma, the partial with respect to x. And those guys are perpendicular. So the gradient vector is perpendicular to the level curves. Is perpendicular to the level curves. So for example, consider the function f(x,y) equal to square root x squared minus y squared, has contour map So we drew this one before, and the contour map looked like this. So we had this x here for f equal to 0. And then we had these hyperbolas for x equal to 1 and 2. So 1, 2, 3. So that's f equal to 1, f equal to 2, f equal to 3. And these are the points 1, 2, 3 on the x-axis, the y-axis, and then you have, of course, the opposite picture over here. So now several gradient vectors are going to be shown here. And the path they indicate. So here, right, gradient vectors are going to be perpendicular. So it looks kind of like that. And the gradient vectors represent the greatest direction of increase. The gradient vector is the largest directional derivative, and it's also perpendicular to the level curves. So the path of steepest increase along a surface follows the gradient of f. And the path of steepest decrease of fx. So the path of steepest increase of fxy on its surface follows the gradient of f. And the path of steepest decrease of fxy on its surface follows, well, the opposite of that, the negative of the gradient. So whenever you see contour maps, if you want the steepest direction of increase or steepest directions of decrease, you just follow the gradient, or you go in the opposite direction of the gradient. So these guys are all perpendicular to the level curves. And you're going to follow this steepest path upward, or this steepest path upward, or this steepest path downward. Right. So where do we see such things in the natural world? So, for example, given a map showing curves of elevation, okay, water will typically flow down in the steepest direction. Will typically follow the gradient, the negative of the gradient f, to go along the path of steepest decrease. Or on a map showing, level curves for atmospheric pressure, okay, the wind will typically flow down the gradient as well. Down the steepest decrease in pressure. That is the negative of the gradient of f. Now, of course, there's going to be other factors at play when you're talking about water flowing downhill or, or with wind or things like that, but it does give you a rough indication of where these things would happen. So like a stream running down the mountain is typically going to follow the steepest line of decrease that it can find. Okay, so that's the gradient. It's pretty neat. And that's the end of this lecture on this section.